Welcome, this is the lesson on the set builder notation. Let's start off with some vocabulary. A set is a collection of things. In our case, they're going to be usually numbers. For example, you're going to see these fancy brackets. Then you're going to see 1, 3, 5, 7, 9. Close the fancy bracket. We would say this is a set of odd numbers from 1 to 10. You could also see it like this. Fancy bracket. 2, 4, 6, 8, 10, close the fancy bracket. We will say this is a set of all even numbers from 1 to 10. The set is just a list of numbers that is grouped using these fancy brackets. So, what is set builder notation? Okay, rather than write all of this out, we can put it in a fancy notation. In this case, this is red. The fancy bracket, which is yellow, is called the set of. The next thing is your variable. You can say all of x. The bar that separates them gives them the condition. So it says such that, and this is the condition, which is x is greater than 0. So this whole thing translates to, it is the sets of all x's such that x is greater than 0. In other words, this is any value that is greater than 0. So when you see this whole thing captures every single number that is greater than 0. So it's 0.1, 0.2, 1, 4, 5, 8, 8.9, pi, 1.33333, any number that is greater than 0. Okay? This set, right, is a way to describe all of them in one thing. Alright, so some examples of set builder notation. Let's say we have this set, 1, 2, 3, so on, so on. We would say that in set builder notation would be the sets of all x, right? That's the x, such that, that's the black bar, and the condition, x is greater than 0 but less than 10. Alright, so what you saw is that it's the type of numbers. So in this case, you're going to see this, something like this. This is going to be translated to the sets of all x that are members of the real number, which is that, such that, which is the black bar, here's the condition, that x is greater than or equal to 3. In other words, these are all the real numbers from 3 and upward. Alright, so the first one, you deal with natural numbers. Natural numbers are physical numbers that you can count in nature. Okay. Here is what it would look like in the list format. So it can be 1, 2, 3, 4, 5, 6, and so on. In the set notation, you just put it in the fancy bracket and separate each thing by a comma. Each term here are called elements within that set. So this is the first element, this is the second element, this is the third element, okay? So in set builder notation, you could say this. This is the set of all x such that x are members of the natural number and is greater than 0. Okay? So, once we have the natural numbers, we wanted to make 0. So, once they introduce 0, it becomes the whole number. So, you would see it using as a W. So, this reads, the sets of all x such that x is an element, right, or member of the whole numbers. Okay, so if you see this, it refers to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on and so on. Okay, it is the set of all whole numbers. Next, after we make 0, right, we wanted to now introduce the negative numbers so we can start subtracting. So you could have things like -7, -6, -5, 4, -4, so on, so on. Put that in set notation. You can combine it into set builder notation. You use the symbol of that z. You can say the sets of all x such that they are members of the integer. So if you see this, it means this. -7, -6, -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, so on. These are all the integers. Okay? That's what this set means. Next, you could also see this where they just cut off the negative. You would say that it is the set of all x such that they are the members of the integer and that are greater than or equal to 0. Okay, so it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 11, 12. If you ever see this, this is just another way of saying whole numbers. Okay? Next, We already know how to add and subtract, right? Those are your natural numbers, then your whole numbers. Now, when they start to divide, you get these things called rational numbers, okay? You get 1/2, 5 over 2, negative 6 over 5, right? This is how it would look like in set notation. So once you start dividing and having fractions, right? Fractions that stop, okay? You could put it in this notation using this Q. You can say this is the set of all x such that they are members of the rational numbers. Next, once we start dividing, there are some numbers that go on forever, right? Like 1/3, which is 0.3333, goes on forever, or pi, which is 3.14, right? It didn't make sense to the people that came up with it. They're like, how can a number not stop? This is why they call it the irrational numbers, okay? Right? Oops, sorry. This is the rational numbers cutting off with 0, right? This is what the irrational numbers are. Once you bring all the irrational numbers, right, which are just numbers that go on forever, and you put them into the regular set, we call those the real numbers. So the real numbers are every single number that you deal with in up to high school until you start dealing with things called complex numbers or imaginary numbers. But for right now, real numbers are every single number that you can play with right now. Okay? So this is what it looks like in set notation. We can say this is the sets of all x such that x are members of the real number. That's why they use that fancy R. You could cut that off by just using 0 and moving forward, right? You're cutting off all the negatives. You could put this in set builder notation, saying x is all the real numbers such that x is greater than or equal to 0. Notice this is 0, the fractions that stop and the fraction that goes on forever, right? So these are the real numbers. But remember, when you deal with just rational numbers, which is q, you get the finite fractions, which is 1/2, 1/4, right? You don't get the ones that go on forever. Okay, so that's it. These are all the real numbers, and that is what set builder notation is. It's a way of describing a bunch of numbers in a little notation. Okay, all right, there you go.